All right, so well, thanks for joining today. I have been working with Lev on some use cases the past few months, and one of them that came up was forecasting for our call center daily call volume. And so we kind of been working on this approach using tree-based ensembles. And so the topic of this particular presentation is how to do time series forecasting with kind of an alternative method compared to traditional statistical or time series methods that you may be familiar with. So just quickly about me, my name is Brett Efaw. I'm a data scientist at Idaho Power. We're a power utility in Idaho. It's a pretty straightforward name there, but I work with a lot of our different business groups across the enterprise to help them implement different data science for advanced analytics solutions. And one of those, like I mentioned, is forecasting daily call volume for our call center. So that's kind of the motivation of this particular presentation. So in terms of agenda, I'll spend a little bit of time just talking about traditional statistical or time series methods versus more of a machine learning approach to the problem, the non-deep learning kind of stuff. There's definitely some deep learning approaches you can take out there, particularly LSTM and RNN architectures have been shown to be useful for time series forecasting. But what I'll be talking about today is using tree-based ensembles to make forecasts. And the data that I'm working with here is a simulated data set in Python, and we'll have a notebook that I can post to either Lev's repo or the Google Drive if anybody wants to take a look at it and play around with that. And then we'll kind of walk through the basic premise of how to make that tree-based forecast and a particular step that you might have to do to address some of the challenges that tree-based ensembles can have in forecasting, particularly fitting and forecasting the trend. And then we'll compare this to a traditional method like ARIMA, see how they compare. So first, on kind of traditional forecasting methods, there's kind of the bare minimum, or kind of the, at least the introductory thing you can do is essentially treat your date or time index as your input feature, your X variable. And then the thing you're trying to forecast, your Y variable, your target, you just simply regress it, X on Y. And then when you make forecasts, you're just extrapolating outside the range of X, or the date or the time. In practice, you usually will have time series data that's a little bit more complicated than what a simple linear regression can model. And so typically you'll kind of start out or get to time series methods that are all kind of based on this concept of predicting future values based on past values, essentially taking advantage of the fact that you know the order of the data. And so autoregressive, self-regression, regressing past values onto future values, or regressing the data set onto itself is where that terminology comes from. So to do time series forecasting with kind of a more classic machine learning approach, instead of necessarily building features from past values of the target variable, what you can do is extract components from the calendar as features. And so if you have, let's say, daily or sub-daily data, there's a whole suite of features you can extract from knowing that calendar date or time. I just listed some examples here. Some of these features are cyclic in nature, like day of the week, day of the month, day of the year. Some of them are kind of human driven, like day of the week is just something that humans created and invented, and we kind of all just follow that pattern. Some of them are more grounded in kind of physics. Hour of the day is the Earth rotating, day of the year is the Earth going around the sun, things like that. But the point is, if you know the calendar date or the time that something is occurring at, you can extract a bunch of features from that and use it in your machine learning algorithm. And I guess it kind of goes without saying that the reason why this works is because we know what these features are going to be in the future. If we know that today's Friday, we know with a great deal of certainty that tomorrow is going to be Saturday, and so on. So we're kind of taking advantage of the fact that these features are known for the time period or the data set that we're trying to make these forecasts for. So we can calculate them at the time we build the model. So here's our little simulated data set. Again, I've got a notebook that will accompany this if you want to dig into the details more, but just basically using Panda's date range method to create 3 years of daily data, and then adding some random noise, a linear trend across the whole 3 years, some positive and negative events to kind of simulate things like holidays or marketing campaigns, whatever could be applicable for whatever data set you're working with. And then a couple of cyclic features, in particular day of the week, day of the month, day of the year, which you can just extract from that date. I also created in this little data set here a sign representation of those three as well, which you can use on the machine learning side. Tree-based ensembles don't really need the features to be scaled, but some other algorithms do. So using a trigonometric conversion of those components could be useful. I created these just to simply create some signal in the target variable that we can try to model. And so the target variable is just basically adding all these things up: the trend, the multi-seasonal components, the day of the week, day of the month, day of the year, some up-down noise, up-down events, and then some random noise. So here's what the data set looks like visually. Each one of these components, we've got a trend, these up-down events, which in this data set are random, but in reality, you know what these are. They'd be impacts, either positive or negative, because of a holiday or whatever. And then some noise. These are also offset in the graph, just so we can look at them a little bit easier. And then here's the cyclic features, day of the week, day of the month, day of the year, using in the sine, trigonometric scale. So kind of a high frequency, medium, low frequency signal. And then here are those same three on their kind of their integer normal scale of 1 to 7, 1 to 31, 1 to 366 for day of the year. And then here's the final simulated data set. So we've got this upward trend. It's a nice linear trend. We made it that way, obviously. But it also has these overlapping seasonal patterns of the day of the week, kind of the day of the month, you can kind of see in there, and then these kind of bigger ones for day of the year. And if you zoom in close enough and you line the events, you can kind of see where those events also kind of produce positive and negative spikes in the data. So before we get into kind of the methodology, just another concept with time series forecasting, and that's time series splitting, which is basically like cross-validation, but for time series data or ordered data. And so the primary use of this is to evaluate how accurate a particular model or modeling approach you have for a particular data set. And where it differs from typical cross-validation is instead of randomly partitioning your data or folding your data, you want to preserve the order, because when you build a model on a time series data set and then make forecasts, you would never randomly drop data that you would exclude out of your training data set. So you want to try to keep those training and test partitions kind of chunks in their particular order. And so that graph on the right there from scikit-learn kind of visualizes what you would do with different where the data is arranged. You know, the training data set always comes before the test data set in terms of its sequence. And so scikit-learn model selection library has a time series split method that you can use to make convenient splits for whatever time series you're working with. And this can be, you can use this with machine learning methods or traditional time series methods. Anything will work with these. This method just produces the indices to go split up your data. So now just a quick little discussion on tree-based ensembles. So this is the machine learning, classic machine learning technique that we've been using for this particular problem. And so tree-based ensembles are essentially an extension of decision trees, a decision tree algorithm. And it's a way to combine lots of different decision trees or iterations of decision trees, essentially boosting or improving the predictive performance of a single tree. And the two most commonly used implementations of tree-based ensembles would probably be random forests, which is a bagging algorithm, bootstrap aggregating, and gradient boosting. And so scikit-learn has two implementations of these that are really useful, that I use quite often for lots of different problems. A couple just key notes on these ensemble methods for tree-based algorithm. They can handle different types of inputs, and also you don't really have to worry too much about feature scaling or normalization. They're also pretty fast and fairly robust to different types of issues like outliers or missing data. They do have, however, one kind of fundamental drawback that's really specific in terms of a potential problem when it comes to forecasting, and that's they can't extrapolate outside the range of past values or the historical data that you train it on. So as a simple example, let's say we have this data set with 100 data points. It's a linear trend going up at a constant rate. And we train a tree-based model on the first 90 points, and then we try to predict the last 10 points. That model would literally be capped for this, pretty simple, easy data set at the maximum value in the training data set, everything left of that dashed line. And so when it comes time to make predictions, it's just kind of stuck there. It says, I didn't see anything bigger than 0.8 in this training data set, so that's all I can predict. It can't extrapolate beyond that range of past values. So in a forecasting context, that can be potentially an issue if your data set is trending up or down, and you might have to make forecasts outside the range of past values. So as we get into this, we'll kind of see how we can try to address that. And the basic approach is we break down the modeling process into two steps. We first address the trend, and it can be a simple or more complicated method, and we'll talk a little bit more about that at the end. But the basic idea is we take the target variable, and like the day number, the row sequence, whatever granularity our data is at, could be hour or whatever, but we try to fit some kind of model to explain the trend in the data. And then once we have that, we detrend our past data, and then we use our tree-based ensemble model on the detrended target variable as a function of all these cyclic calendar features like day of the week, day of the month, day of the year, anything else we think might be relevant for that particular problem. And so getting a little bit more into the exact steps. First, we fit a trend to the past data using whatever method we think is most appropriate. Then we predict that trend into the future, the test partition or the test split. And those two could be the same method or they could be different methods. Then once we have the fitted values for the training data set, we detrend the past or those past values. And then we fit our tree-based ensemble on the detrended target using all those calendar features. Then we apply that model to the test data set, the feature or the test partition. And then we have these two different sets of predictions. We have the trend prediction and we have the tree-based or tree model prediction. And when we combine those, we add them together. That's our final forecast. So it's a fairly straightforward process. The big kind of question or the big kind of variable on how you would approach this is, well, how do you fit and potentially different way to forecast the trend? And so there's as many different methods that you could probably come up with. We could have listed here, but you could use linear regression, polynomial regression, some kind of non-parametric regression, maybe seasonal decomposition. You could potentially aggregate to a lower frequency time series and use maybe a traditional statistic or a time series method like ARIMA to fit the trend. You could do signal time series signal filtering. You could potentially do nothing. If you don't think your time series is trending up or down significantly, then you may not have to address it. And so you could take a lot of artistic integrity or artistic license to address the trend. Not too far. So let's just assume back to our simulated data set, we'll just say linear regression. We'll use that to address the trend. And it, in this case, works really well because that's exactly the type of trend we have because we simulated it. But what would that actually look like? So here's one of the splits for the simulated data set. The red line's the fitted trend to the training split, and then the blue line at the end there's what we would forecast the trend to be doing, and then the black's the actual values. So then once we've detrended the past, they should be the time series at that point is fairly flat. It can and in all likelihood will exhibit seasonal variation still, and that's okay, that's fine. We're not trying to model all that seasonal variation because our tree-based ensemble should be able to figure that stuff out. So as you can see in this, even though it's detrended, there's still patterns of day of the week, day of the month, day of the year type stuff going on. So we don't have to necessarily try to get this completely explained with the trend step. The whole goal of this is to try to get this detrended data so that when we make predictions with the tree-based ensemble, we're not really in danger of having to extend beyond the min and max of this particular training data set. So we want to be able to keep that bounded within the range of past values. So then we fit a tree-based ensemble like gradient boosting or random forest on the detrended data, and then we have our trend forecast or trend prediction. We have a tree-based prediction, and we just add those two up together, and we get a nice forecast on the original scale of the data. Another useful component or I guess aspect of using a tree-based model is that you can calculate feature importance fairly easily. And so if sometimes when you build forecasting models and make forecasts for, if you work in a business or whatever, and they say, well, how come the model makes forecasts like that? Or why is it, what's kind of driving that? And so getting feature importance, even though we can't really control the calendar features all that much, it is sometimes useful to get in there and say, oh, we have a really strong, day of the week pattern, but not so much for maybe something else like day of the month. In our simulated data set, they were all kind of equally important by design, because that's how we built the simulated target. But anyway, that's another nice outcome that you can get from tree-based models. So we also wanted to kind of compare this. We talked about at the beginning, comparing this to a traditional time series approach, and ARIMA is probably one of the most commonly used traditional time series methodologies out there. And so ARIMA stands for autoregressive integrated moving average. If you haven't heard of that before, but it's basically combining this notion of predicting future values based on lags of the target, the autoregressive component, the error component, with some moving average component of the data. So kind of addressing that trend, if you will, with moving average. And so Python has a lot of, can fit ARIMA models. And also I found a package out there that you may be familiar with or may have used in the past called PMD ARIMA, and it essentially wraps the time series ARIMA function with an algorithm that Rob Hyndman came up with to find the best parameters for an ARIMA model. And so if you ever want to get more into kind of ARIMA and time series in general, Rob has these two versions of the same online textbook called Forecasting Principles in Practice, and I would highly recommend checking those out. They're free and filled with tons of great stuff. The only I guess potential thing is he's an R guy, so he has all these in R. He's authored a lot of R packages, so if you're Python, it might be a little bit challenging. But the two versions of the two different kind of R packages he's authored. But Auto ARIMA and the PMD ARIMA package essentially follows the same philosophy for finding the best ARIMA model. So for our simulated data set, I went through and applied the Auto ARIMA function to it for each of the splits. And here's the first split. And generally speaking, across all these splits, and again, you can go check out this notebook if you want to kind of dig into the details more, but the Auto ARIMA did a pretty good job figuring out the dominant, or at least the highest frequency seasonality, the day of the week one, but it generally figured out the trend as well, but it kind of failed at getting all three seasonal components figured out, which makes sense. ARIMA is not really a multi-seasonal algorithm, so it's not really surprising that I kind of struggled with that a little bit. And here's zooming in on one of the splits just to compare, what the ARIMA forecast looked like, and then what the tree-based ensemble with the trend looked like. And across the entire simulated data set with 10 splits, the tree-based performance was a little bit better, around 11% error, where the Auto ARIMA was up towards 20% error. But even looking at the error of those two, we could probably fine-tune the ARIMA a little bit and get that performing better. Maybe not train it on so much history, just kind of focus on the dominant at that point, the dominant seasonality. But the other thing that was big out of this is just the time to train. On my machine, it took about 15 seconds to go through all 10 splits to detrend them and then fit the tree-based model, whereas the Auto ARIMA algorithm took about a minute per split to kind of go through and figure out what the best ARIMA parameters were. So that could also potentially be something to consider when you're actually doing this for real. And then before we end, I just wanted to put a little note out there on kind of the trend with with a real data set. So this data set here, this is daily call volume for one of our queues in our call center, and the red line here is the linear trend, which in this case it works pretty well. That's kind of a good representation of the long-term trend, just very slightly decreasing if mostly just flat. But you could potentially use other methods to kind of figure out the trend. In this case, I used a signal filter from a SciPy signal processing module to kind of fit that blue line in there. And so, you could potentially get more sophisticated or advanced based on what kind of method you throw at the trend problem. So to wrap up, basically we just kind of went through this general process to apply a tree-based ensemble approach to time series forecasting as opposed to maybe a more traditional statistical method. Basically, the most interesting component of that is you use calendar features as or calendar-based features for the machine learning model, and then potentially have to address the trend because those models might not be able to extrapolate. A couple other things that would also potentially go into a real-world problem is tuning the tree-based algo. I just use the defaults in the notebook if you go look at that, but in reality, you'd probably want to go through the different tuning parameters and try to figure out which ones work best for your particular data set. And then, there's just lots of other options in terms of the feature engineering piece of the date components. And this really comes into play when you have more high frequency time series like sub-daily, like hourly. You can extract a lot of components, and you could potentially even build in lags of the target variable and still use the same approach that you would use like a random forest or whatever. And then some other just kind of general considerations is the time series regular or irregular. Some of the traditional statistical time series methods kind of struggle with irregular time series, whereas traditional machine learning approach, it doesn't really matter if the data, you skip weekends or you skip a day here or there, or you have randomly missing hours. It doesn't really matter. And then also just kind of ease of implementing it or automating it if you're trying to build lots of forecasts for lots of different time series. Something like a tree-based algo that can fit a model in 5 seconds or less might be desirable compared to trying to use auto ARIMA that may take a minute or two. And then I also just provided this little diagram here on the right. This is kind of like I would say sort of my personal decision tree on which sort of method I would lean towards if I were to try to build a forecasting model. And it kind of comes down to initially, what's the frequency of the time series? If it's low frequency, meaning kind of monthly, quarterly, annual, the traditional methods like ARIMA, ETS, exponential smoothing, they're kind of built for that. So, I predominantly just stick with those if I have low frequency data. But if I have high frequency data like daily, maybe hourly or sub-daily, at some 4 times a day or whatever, then you can start getting into, well, maybe a tree-based algorithm is more appropriate or would work better, especially if the time series is irregular. It skips days or skips hours, or it doesn't have regularly spaced time points. And then also just kind of considering how much autocorrelation there is. If you do have a lot of autocorrelation in the time series, like for example, the value at time point t is strongly correlated with the value at time point t minus 1 or 2, even though you may have high frequency data, a traditional ARIMA type method might work best. Whereas if your data is not really following that much or doesn't have that much autocorrelation, but more has these overlapping cyclic signals or patterns based on day of the week or hour of the day or whatever. Those tree-based methods are kind of the way I would lean. So that's it for me. I'll open it up for any questions or comments. And I guess first I should stop recording.
No, don't stop recording. Brett, thank you very much. It was very good. I want to add something. So first of all, when you're using features, which is like multiple columns, right?
Mhm.
You can easily add features, which, as you did, you added some events, which were short like events, but you can also add long events, like some sort of I don't know, COVID or drought, like some extreme weather or like some extreme events, and you can incorporate them like historically, and this will help you to like make better model, right?
Yes, absolutely. Yeah, we had one example is back to the call center. Different things that we may implement. We had right around when COVID started, we didn't do remote disconnects. So one of our queues, basically had a big change for a couple of months, and so we put that into that particular model and said, everything between these two dates was, we were operating under this particular set of rules or whatever, and then it changed, and so then that becomes a feature in your model. Yeah.
Right. And another thing, in ARIMA world, there is actually a variation of ARIMA model which does similar thing. There is ARIMA-X, which does exactly that. It allows you to add extra column, exogenous factors. And another is SARIMAX, where S stands for seasonality. And maybe using S for seasonality and X for exogenous, you can make ARIMA work better. But still, the simple approach of this tree ensemble is just so simple, so easy to understand, and so fast to train. And another thing is that if you want to add lagged variables into tree model, you can, right? but still, you will have better control and better understanding of the model. So I think, Brett, what you demonstrated here on synthetic data is like very easy to see how the model works, and I know that you already like used it for real data and it works very well, so just congratulations.
No, it's those are all those, ease of implementation, ease of understanding, would be definite pros for the tree-based ensemble approach.
Yeah, and thank you very much for coming for the seminar. This is your first experience, but hopefully not the last one.
No, this was great. I appreciate it. I've attended a couple in the past, but hopefully we'll be able to get some more presentations put together for future topics.
Thank you. So let's stop the recording then, and